Hello guys, and welcome back to Fun with Neural Networks. Today we look at backpropagation, which is the reason the entire series was born in the first place. Now, disclaimer is that I am using the exact equations from the DeepLearning.AI course on Coursera, taught by my personal hero, Andrew Ng, but the main general idea behind backpropagation is preserved. Alright, let's get to it. Now, we left off having Bill's intuition about forward propagation and how information is propagated from the input all the way to predictions, and we compute our loss, which is how wrong we're getting our predictions. So now we're going to be going backwards, right? Using calculus. We're going to use a lot of calculus, so spoiler ahead. So as usual, we're going to be exploring the math, not the explanations, because there's a richer explanation on the in the course. Now let's have a place for our handy rules right over here, and the first of such rules that we're going to be using is that ddx, that is the derivative of a function that looks like a log of x, is a over x, right? So that's our first rule. All right, cool. We're going to be using chain rule, a lot of it, so that's another spoiler. So starting from our loss, we have that loss equals negative y log y hat plus 1 minus y log 1 minus y hat. Okay, so the derivative of the loss with respect to y hat, which is really saying how much does our loss change when we change our predictions, right? Makes a lot of sense. Okay, so dl dy hat, and this looks like this, right? Where negative y is like our a and x is our y hat. And so we could say negative y over y hat plus, same thing here, a is 1 minus y and x is 1 minus y hat. And so we have 1 minus y over 1 minus y hat. Okay, we could simplify this using regular algebra, where we have y hat 1 minus y hat, and we work it out to be negative y 1 minus y hat, correct, plus y hat 1 minus y over y hat 1 minus y hat. That looks like a straight line. All right, cool. So we can expand this once again. We get y, negative y, plus y hat plus y hat, negative y hat over, wow, over y hat 1 minus y hat. All right, looking good. And so from here, we could see that we have a positive y hat and a negative y hat. So that they can't stay in the same place, right? They need to execute each other. All right, so we're left with y hat negative y over y hat 1 minus y hat. All right, this looks like a good place to stop. dl dy hat. And like we've said, it's that y hat is really the same thing as a2, and so this is the same thing as saying as dl dA2 equals, it's a stretch writing a2. I'm sorry, that's actually correct. Minus y over a2 1 minus a2, but this is a stretch. I'm not gonna write it, but it's the same thing, right? Because y hat really is equal to a2. All right, we can use our red pen to say check. We have dl dA2. This is just at a point where I've not worked it out just yet, but yeah, moving on. Moving on, this we have to find DLDZ2. And so this is where chain rule comes into play, right? And so chain rule says when we have a function, right? When we have a function f of x that's an input to another function, so say g of x. So f of x is an input to g of x, right? The derivative of this really is worked out to be, according to chain rule, let's work it out. G prime of f of x is worked out to be g prime of f of x multiplied by f prime of x. And it's really the derivative of the outside function multiplied by the derivative of the inside function, right? And relating this to our goal, which is the LDZ2, and we have seen how Z2, let's go back here, we see how Z2 is inside of A2, and we're trying to relate, and A2 is inside of L, and we're trying to find a relationship between L and Z2. How much does our L change when we nudge Z2? Okay, so that gets us to saying that, so I'm going to write down the entire equation, right? So it's going to be something like negative y log of g of z2, right? Does it make sense? Plus 1 minus y log of 1 minus g of z2. Running out of space here, right? That's not the derivative. I'm just writing down the loss function in terms of z2. All right, let's get rid of that. That was just for demonstration purposes. And so dl dz2, if we say the inside function multiplied by the outside function, so it's something like dl dA2, tell me if this makes any sense, multiplied by dA2 dz2, right? The outside function multiplied by the inside function. And we have already worked out the outside function. It's what? It's y hat. Or at this point, I'm going to use, you know what? I'm going to use y hat. It's the same thing. They are interchangeable. Y hat minus y over y hat 1 minus y hat multiplied by, now, the derivative here. And remember, the function is of what? Sigmoid type. And we did a derivative of any sigmoid function, right? And we worked it out to be that, it worked out to be that the derivative of a sigmoid function is the same thing as the output multiplied by 1 minus the output itself. And so in this case, A2 multiplied by 1 minus A2, or y hat multiplied by 1 minus y hat. And so we write that down, y hat multiplied by 1 minus y hat. And hey, look, remember I told you it's going to be very handy for us later down the line, and here it is. So we're going to go away with these two. So we're left with y hat negative y. And so this is dl dz2. All right, looking good so far. And we have that. Same thing as, if we want it this way, A2 minus y, all right? It's just our predictions minus the true values, all right? So everything is working out. Then we take our red pen and say check. All right, going on down the tree, next up we have DL-DW2, right? And we do the same thing. We just take it up another level. We say DL-DW2 is equal to DL-DZ2 multiplied by DZ2 over DW2, right? And we have worked out DZ2, DL-DZ2 as this. So we're not going to write it down. We're going to use a shorthand, right? Shorthand for this is written as DZ2, right? Shorthand for this would be DA2, just to keep that in mind. And so instead of writing DL DZ2, we just write DZ2. Let's get a separator over here. We just write the DZ2 multiplied by DZ DW2. If we take a look at this, we look at the relationship between Z2 and W2, and we see that the derivative would be A1, right? So we go here, DZ2 times A1. Is that what we have over here? Yes. And so we take our red pen and we say check. All right, moving on, looking good, and moving on. Now, next up, we're going to look for DB2, right? So we have DL, DB2, really would be DL, DZ2, multiplied by DZ2, DB2. We already have this, so we're just going to write down DZ2 multiplied by, let's look up the relationship between Z and B, and we could see that the derivative would be 1, right? So let's go back, 1, and that's it. So let's look out. I keep saying look out. Let's look up what our DB2 is, see if it's equal to this. We go over there, and it in fact is. Okay, take our red pen, and we say check. All right, next up, we have DL, DA1, right? Also can be worked out as DL, DZ2, right? Multiplied by DZ2, DA1, right? This, we already have it as DZ2. Use our shorthand, multiplied by, let's go back and look up the relationship between Z2 and A1, and it's what? Z2 and A1. We see that the derivative is W2 transpose. We come here, we say W2 transpose, and let's check if we are correct, right? And the order is changed just for the matrix multiplication to work out, so we're still correct. So we use our red pen and say check. Okay, I'm having to span a lot here. Okay, moving on, we're going to look for DL, DZ1, and this would in fact be DL, DA1, right? Multiplied by DA1, DZ1, right? We already have this as DA1, multiplied by, let's look up the relationship between these two. And if we do, we're going to find out it's the same sigmoid, right? It's the same sigmoid function, and we could write it down that way, or we could just say g prime of z1. And this would be a general way, a better way to write it, because not all the time that we use the same sigmoid function. We could use, this could be a ReLU, and so this would just be a derivative of the ReLU function. ReLU is another activation function. Or softmax, whatever it is, it could be any activation function, and here we're just taking the derivative of that activation function. But since this, we are using sigmoid, this is the same thing as dA1 multiplied by A1 1 minus A1, right? So I'm going to start this, and let's see if we're correct. I'm very sure we're correct, but just for emphasis, let's go back and see. We have this, right? And we look about correct, right? dA1 times inverse of the activation function. All right, red pen as usual, check. And let's go next, dl, dw1, really same thing as dl, dz1 times dz1 dw1, right? We already have this as dz1 multiplied by, let's look up the relationship between these two, z1 and w1, and it is in fact x. Okay, sorry, z1 and w1, yeah, and it's in fact x. Okay, whoa, okay, it's x. But for the matrix multiplication to work out, we add a little transpose over here. And I'm sure we're correct, but let's check it out. dz1 times x transpose. Okay, another barrier over here. And finally, we have dl db1, which is the same thing as dl dz1 by dz1 db1. Okay, we already have this as dz1, and we multiply it by, let's look up the relationship between z and b. You're not meant to move. All right, relationship between z and b, the derivative would be 1, right? Okay, multiplied by 1, right? And like I'm always sure we're correct, well, let's check. We have that. Okay, and as a side note, we're basically done. We've worked out all of the equations, but as a side note, we're not just coming up with dz or dA from nowhere, you know. It's really coming all the way from dl, right? We're coming all the way from there, because it's really like this. Sorry about that. What we have been doing is dl dA2 times dA2 dz1, right, times dz1 over dA1, right? I'm sorry, this is 2, right, times dA1 over dz1, right? that's basically what we have always been doing. And this is what DZ1 stands for. So it's coming all the way from at L and coming to Z, because this goes out with this goes out with this goes out with this, and we have this, right? And so it's just quicker to write it this way. All right. Thank you very much for being on this journey with me. I know that figuring this out is a bit tricky, right? But I hope that this video has helped you out. If you are anything like me when you were taking the deep learning course, then this would have been very, very helpful, right? And all right, this wraps it up for fun with neural networks.